As a car travels along a narrow city street, reflections of the glossy paint or side mirrors of parked vehicles can help the driver glimpse things that would otherwise be hidden from view, like a child playing on the sidewalk behind the parked cars. Drawing on this idea, researchers from MIT and Rice University have created a computer vision technique that leverages reflections to image the world. Their method uses reflections to turn glossy objects into cameras, enabling a user to see the world as if they were looking through the lenses of everyday objects like a ceramic coffee mug or a metallic paperweight. Using images of an object taken from different angles, the technique converts the surface of that object into a virtual sensor which captures reflections. The AI system maps these reflections in a way that enables it to estimate depth in the scene and capture novel views that would only be visible from the object's perspective. One could use this technique to see around corners or beyond objects that block the observer's view. This method could be especially useful in autonomous vehicles. For instance, it could enable a self-driving car to use reflections from objects it passes, like lampposts or buildings, to see around a parked truck. The heroes in crime television shows often zoom and enhance surveillance footage to capture reflections, perhaps those caught in a suspect's sunglasses, that help them solve a crime. In real life, exploiting these reflections is not as easy as just pushing an enhance button. Getting useful information out of these reflections is pretty hard because reflections give us a distorted view of the world. This distortion depends on the shape of the object and the world that object is reflecting, both of which researchers may have incomplete information about. In addition, the glossy object may have its own color and texture that mixes with reflections. Plus, reflections are two-dimensional projections of a three-dimensional world, which makes it hard to judge depth in reflected scenes. The researchers found a way to overcome these challenges. Their technique, known as ORCa, which stands for Objects as Radiance-Field Cameras, works in 3 steps. First, they take pictures of an object from many vantage points, capturing multiple reflections on the glossy object. Then, for each image from the real camera, ORCa uses machine learning to convert the surface of the object into a virtual sensor that captures light and reflections that strike each virtual pixel on the object's surface. Finally, the system uses virtual pixels on the object's surface to model the 3D environment from the point of view of the object. Imaging the object from many angles enables ORCa to capture multi-view reflections, which the system uses to establish depth between the glossy object and other objects in the scene, in addition to estimating the shape of the glossy object. ORCa models the scene as a 5D radiance field, which captures additional information about the intensity and direction of light rays that emanate from and strike each point in the scene. The additional information contained in this 5D radiance field also helps ORCa accurately estimate depth. And because the scene is represented as a 5D radiance field rather than a 2D image, the user can see hidden features that would otherwise be blocked by corners or obstructions. In fact, once ORCa has captured this 5D radiance field, the user can put a virtual camera anywhere in the scene and synthesize what that camera would see. The user would also insert virtual objects into the environment or change the appearance of an object, such as from ceramic to metallic. The researchers evaluated their technique by comparing it with the other methods that model reflections, which is a slightly different task than ORCa performs. Their method performed well at separating out the true color of an object from the reflections, and it outperformed the baselines by extracting more accurate object geometry and textures. They compared the system's depth estimations with simulated ground truth data on the actual distance between objects in the scene and found ORCa's predictions to be reliable. Consistently with ORCa, it not only estimates the environment accurately as a 5D image, but to achieve that in the intermediate steps, it also does a good job estimating the shape of the object and separating the reflections from the object texture. Building off of this proof of concept, the researchers want to apply this technique to drone imaging. ORCa could use faint reflections from objects a drone flies over to reconstruct a scene from the ground. They also want to enhance ORCa so it can utilize other cues such as shadows to reconstruct hidden information or combine reflections from two objects to image new parts of a scene.